first, to run any Jupyter Notebook, you need a server to run it on. So this can be just your local laptop, or if you want to use a GPU or a cluster, you'll have to start the server on the cluster and then connect your whatever runtime you have. So in my case, I am using OpenMind. So I SSH into OpenMind, and I can do this for you here. And in my folder that I'm working in, I've created a batch file to schedule a Slurm job. So Slurm is the scheduler, the job scheduler used on OpenMind to acquire resources. And I will show you the batch file here. So this file is used to acquire given resources, and you can change how many GPUs you want, for example, or how many threads, essentially cores of the CPU you're using, constrain the type of GPU you want, and a couple different like OS constraints, for example, and memory constraints. So all of this is on the wiki, and I've linked that in the Collab notebook for you guys to check out how to do this more specifically for whatever needs you have. This essentially activates a Conda environment and boots up a Jupyter server. So then you'll call this batch script using sbatch jupyter.sh or whatever you want to call your file. And it will, and I've already done this, so it'll show up here when you do type the command sq-u for user and your username. And then an output file called that you can specify, I've called it jupyter.out, will be created. And of course it's nonsensical now because I've been using it for a while, but all right, that is unnecessary. Sorry, it's just very long. Let's start this again. I'll just take you through this process anyway because the server crashed. So and I'll cancel that other job that we were using. Okay, and then in your output file, you're going to get, see it's now started the Jupyter server. You have to give it about 30 seconds. And it will provide you with a link that you can use to connect to your Jupyter server. So here it is. The second link is the link you want to use. The first tells you what node you're running on. So we're running on node 61. Now we're going to do something called SSH tunneling. This is going to connect our local computer to the node through the host node. And I've created a batch, just a bash script to do this, which essentially allows me to just input my port that I've specified in my batch script and the node. But for reference, this is going to be in this tutorial, how to use Jupyter Notebook on OpenMind. And it just tells you the commands you need to run. for SSH forwarding and for starting up your server. Okay, so now I've done this setup as port forwarding. Now I can connect to the server through Google Colab. You can do this a number of ways. If you prefer using Jupyter Notebook or a Jupyter Lab, just paste the URL straight into your browser, and it will take you to the Jupyter Lab IDE here. Wi-Fi is not great, but while it loads, there we go. Yes. Yes, because I mean, you can run stuff on Colab using the hosted runtime, but because I can't give you the data and there's no way of like hosting the data that the student gave me for you guys to use, you're not going to be able to train the model on his data. So you're welcome to run the scripts, but it's not going to do much for you. If you would like, you can download the AccuSleep dataset, which is I've linked above. It's huge. It's a lot of data, and it's what we're using to pre-train this model. But yeah, for now, I'd say just follow along through the code, but we're not going to be able to run it. Yeah, so essentially, and we'll get into this, but what I did was I used the 24-hour for training and the 4-hour for testing for validation. So yeah, this is if you want to use it in Jupyter Lab, but I prefer using either VS Code or Google Colab. And so to do so, you'll open your notebook, click connect to local runtime, and then paste that URL in. And it'll connect here. And you can see to check, for example, what kind of device you have, a GPU. You will type something like bang, which will execute something in bash, and NVIDIA-SMI. And as you can see, we have 4 GPUs allocated to us. Okay, I'm gonna have to restart this. All right, so I've linked a couple resources here for you guys to use. The wiki, of course, is going to have a bunch of resources if you want to use OpenMind, and specifically the Jupyter Notebook tutorial will teach you how to do what I just did in more detail. There's also the website, which has some slides on basic OpenMind tutorials, and then the data set here that we're going to be using. So now that we're here, a bit of context on the problem that we're going to be trying to solve. This problem is known as sleep staging, and the goal is to use EEG and EMG data, specifically of mice in our case, to predict what stage of sleep a mouse is in. It's like sleep scoring. So the labeled data is labeled with either wake, REM, or non-REM sleep for a given 2.5 second periods. At every 2.5 seconds, there's a label, and this was human labeled, so this is a lot of data. And the student who came to me, who is named Matthias, and he graciously let me use this for the tutorial, but he wanted to use a model pre-trained on these AccuSleep data for his own data set. And so this is kind of the overarching goal of what we're trying to do here today. But a lot of the principles apply to other time series data, for example. So basically, we're going to install any requirements. A good practice is to have something called a requirements.txt file in your repository, which specifies all the necessary Python packages you may need. And an interesting thing about Google Colab is that the notebook that you have that you're using is stored and hosted on Google Drive. But everything else, if you connect to a local runtime, for example, is hosted elsewhere. In my case, it's hosted on OpenMind, where and the current working directory is the folder that I started this batch script in.
Google
Colab offers a bunch of different
services.
So you can also, if you buy, time using their hosted runtimes, you can store your files or your data on Google Drive and then just import them in. Okay, and then for a sanity check, we check that we are on the node that we. What's going on here? All right. Should be working fine, but we're having trouble connecting here. Okay. Perfect. So I've already installed all of these packages, but that's why they say requirement already satisfied, and we are on the correct node, the node that we requested. So here we import a bunch of packages into Python, namely NumPy and Pandas, but mostly we're going to be working with PyTorch tensors. And then this package called Accelerate. So Accelerate is a newer package created by Hugging Face, which allows us to very easily port our PyTorch code into distributed training. So now we can use multiple GPUs to train faster than we would with a single GPU, or even multiple nodes with multiple GPUs on them. And it depends on whatever server you may have. And this is quite useful if you're working with a lot of data, or you're working with data that can't fit, for example, a whole batch onto a single GPU. You can use multiple and split the batches up. So the rest of these, go ahead. I like raw PyTorch. It's just a personal preference. I see no reason not to use PyTorch Lightning if you've been using it before, but really the structure, like the code you write, is fairly similar. And the differences are quite minor. So it's a preference thing. I think Accelerate is super easy if you already have PyTorch code, but say if you already implemented in PyTorch Lightning, which for people that don't know is like higher abstraction, like wrapper for PyTorch, then I mean I would say go ahead and use it. But I don't have like a particular like recommendation either way. It's really your workflow. Yeah, it's very easy, and I'll show you how to do that here. So here we import all these packages that we may need, and we'll go through a couple of them as we go along. And here's where we start the data loading and pre-processing stage. So I've written a couple helper functions here, and namely this class sleep dataset. So PyTorch implements the dataset class, and to implement a custom dataset, you simply create, an inherited class. And here I'm calling it sleep dataset. So this will read our data from wherever we've stored it on our server, and it will structure it in such a way that we can index into it as if it were an array, for example. And this allows us to very easily pull samples from our data set for training. So there are a couple ways you could do this. You could leave all your entire data set in memory, and only load it when you like explicitly need it. And this is a good practice if your data set is huge and doesn't fit on your RAM, and instead you need to keep it on disk until you need a batch, for example, and then you read it from your disk. But turns out that this data set is small enough to fit on 20 gigs, which is what I requested. So I load all of it with a couple functions here. Basically, I won't go into too much detail. If you really would like to, you can go into the code here and see. But what I've done is I have, I run this preprocess script if I haven't done so before. And what this does for me is it does downsampling, it does bandpass filtering, and it does scaling. And all of these are kind of necessary for this EEG domain where data can tend to be noisy and you'll want to clean it up a bit before you make predictions on it. But you don't really want to do this all the time. You don't want to do this, for example, every time you load the data, because this will like make obviously be a pain in the ass to sit there and wait for it to load maybe like 10 minutes of 20 gigs of data into RAM and preprocess all of that on CPU. So instead we preprocess it beforehand, and then we load those preprocessed files afterwards. So now that I've done this in the past, I can always just call this function get preprocessed file, and it'll give us the EEG, EMG, and the labels for each of the directories we specify. The way I structure this is all the EEGs that I've collected for different collection periods, I store in lists as well as the labels. And I create this mapping from essentially the range of total samples that we have, where samples refers to like a single sample is a 2.5 second window. Anywhere in the data set, you pick a window and this is your sample. And this is what you want to predict. Okay, based on this data alone, what stages of sleep is the mouse in? We do a couple different things by extending that window into the past. So we say, look at 10 seconds, what stage were they in the last 2.5 seconds? Giving this context helps with dependencies on like, for example, a mouse can't move from wakefulness to non-REM in one jump. And so having a larger context will kind of get rid of misclassifications. And these considerations are all domain specific. You kind of have to know your data well and be able to make these assumptions. So if you want to do real time, you can't be making predictions based on future time windows, because obviously you won't have seen them until later. So these considerations have to be made for time series data specifically. But that's a little too specific. We'll kind of skip ahead for now. This is the dataset class. It loads all your data into RAM if you want it, and then provides, you have to implement two functions specifically. The length function, which gives you the total number of samples you have, and the get item function. So it gets a single item based on an index that is between 0 and the length of your data set. So again, that index mapping makes this easier, but you can implement this any number of ways. Now we start getting into just loading everything and initializing everything and starting the model design. So these are the parameters that I've specified for our model and for our data and our training paradigm. We'll go through them specifically later, but basically it's a good practice to have a config file. You can store this in a .json or any kind of dictionary that specifies all your configurations so that you can save them later on and reference them in the future if you want to compare different models that you've trained and you want to see, oh, why did this model perform better than another? Okay, now let me run these. So this is the AccuSleep data that we're working with. One is an EEG probe, the other is an EMG probe. And then this is what we're calling the homemade data. This is Matthias's data that he acquired, and we've picked an EEG probe and an EMG probe of his to match. We've downsampled all to the same frequency. We've done all the same pre-processing steps. So theoretically, you want your test data, the data you're hoping to predict on, to be as close in distribution as possible to the training data. It'll lead to, in general, better results. All right, and then I do one more thing here. I create a data set and a data loader to get the input shape of the input size to the model. And this lets you, for example, if you need a specific output shape and you need to use a linear layer to contract the size of a tensor, you're going to need to know the input shape beforehand. And so this is an easy way to do that by just getting the size of the input shape from the data loader. So this data loader class essentially wraps the data set class. And you can see we take sample data, which is our data set, in as a parameter for data loader. And the data loader collates each sample into a batch. So you can specify a batch size to train your model on. Generally, this will be somewhere between 16 and 32, maybe even 64. It depends. You can play around with that number, but this data loader essentially does this for us and will shuffle it for us if we want to. So it can pick random samples from anywhere in the data set and collate them together. A couple different parameters can be specified. So generally, you're going to want to specify or define a function called get data loaders in this accelerate paradigm, because you need to initialize your data loaders, your model, your optimizer, all in the accelerated train function. And so having like a helper function like this that you can save to another file if you want to is a good practice. And essentially just creates your data set, creates the data loaders for each of these data sets, and returns them. And the same goes for fine-tuning. So another thing that we're going to be kind of looking at is this concept of pre-training and fine-tuning. Pre-training is using some large data set that may be kind of agnostic to the task you're working on to train a model to get, a good representation of the task of data that you're working with, the modality of data you're working with. And then you can fine-tune on, say, your own data. And this generally will make for more accurate predictions on your data, because it's kind of, if it's so out of distribution from the training data, you're going to get poor results. And that's kind of what I've seen here, using Matthias's data on a model trained only on the AccuSleep data. All right, so now we're getting into yes. It will, to some degree, there's the benefit of doing this is largely for speed. You will be able to converge faster using the fine-tuned model, or more like what you're saying is true if you don't freeze some parameters of the model. So you could freeze, say, the first half of the model and then train of the pre-trained model, and then only optimize the latter weights for the fine-tuning. And doing so is faster because you're optimizing over less parameters, and it should have some for example, spatial context like developed through the pre-training process. So yeah, it is largely for speed benefits, but you could train even just the last layer, and that's often enough to get the performance you need from like a fine-tuned model. All right, so now we'll get into the actual model design choices. So this data is time series data. And in recent times, attention has often been used. So in the past, these sleep scoring models, they used basic statistical and logistic regression in the beginning, and then slowly moved to convolutional nets. And now, for an experiment, I kind of wanted to try to use attention for it, because attention has been known to be beneficial in training over, say, some time window or context, because the idea of attention is that you attend to different in the context of, LLMs, you attend to different words with different importance based on their similarity to each other. In the same way, you can attend to different time periods in a time series. For example, a large spike in EMG, which would indicate the animal moved a lot. This kind of attention to these very time-specific instances is what makes, theoretically, attention well-suited for time series data. And so I was inspired kind of by audio diffusion. So for people that aren't familiar, diffusion models are what have been used in DALL-E 2, for example, for generative models that generate very detailed and intricate, images after being pre-trained on huge corpus of image data for image generation. And in the audio field, they've started using attention layers to try and achieve a similar effect and improve performance. So this is where I got the idea. Whether or not it is, essential that you have attention in this model is not clear. You can play around with it. I haven't really played around with it, but in the parameters, I specify how many of my blocks have attention implemented, however many of them are just residual convolutional blocks. And that's kind of the general feeling in machine learning, is that you kind of just need to try stuff and figure out what works based on your own task, because there's no free lunch, as we know. So we'll go through this model. Essentially, the basic structure is alternating residual and attention blocks that attend across the temporal dimension, followed by an out block, which is essentially just two linear layers that constrict the output to 3, essentially a tensor of length 3 for our 3 classes. Anyone can stop me if they're confused about some of the neural network modules that we're using, residual, and just ask me questions, because I don't know the experience in the room, so I can clarify anything that people are confused about. Yes. I think this, okay, so the attention mechanism is not precisely how you may think of what biologically or behaviorally what attention is. So it is implemented in, I'll just do
Is that just format annotated that is like a blog post that's kind of explaining?
Yeah, and there are a couple explanations of it, but basically, this is not a great explanation there. This is the mechanism for attention. So the idea of attention that makes it learned are these 3 linear blocks here. So you're not just taking the input and attending to itself, which is what self-attention is, and using like a similarity metric to attend to itself. You are first applying some linear transformation to it and then attending. And this learned linear transformation is what makes the attention learnable. So it's not necessarily attending to a specific portion of your signal simply because it is similar to another portion of your signal. It is doing so because it has learned that in this context, the wait for a spike is important. If you're kind of comprehending my meaning, it's in a way, I mean, that's all ML really is like abstract, is like feature abstraction, but not in a manual way. So I'm struggling a bit to explain this intuitively, without getting into like a ton of math. Yes. Yes. Yeah. The real benefit of this is not really like this like attention. Oh, it can pay attention to different portions. It does this, but it's really like the receptive field, because you're able to attend across the entire sequence at once, where in convolutional blocks you need several layers to get to a point where a token at the end can influence predictions from a token at the beginning. So this speeds up convergence because this receptive field is a little smaller, or is much larger as the entire sequence length. Okay, so let's go back to the model here. All right, so the residual block is the first portion of this, and it's simply, I will also bring up a image here for context. It's a sequence of two convolutional layers with what we call a residual or residual connection. The idea is that by having this residual connection throughout the network, and you do so in the attention module as well, you allow gradients to flow easily from the output to the beginning of the network without something called the decaying gradient, which happens when a network is super deep and the gradient dies out towards the beginning of the network when doing backprop from the loss. There are countless theories as to why this works well. It just works, and that's why we're using it. Doing this, the layers in this diagram here are one-dimensional convolutions. So we're doing convolution across the temporal dimension in our image in our across two channels, and we're increasing the number of channels each time. This is generally supported in the literature. Just by increasing the number of channels, you increase the number of learnable parameters, and you can play around with these. Here we have the forward function. So to implement any module in PyTorch, you need to implement two functions only, two methods only, the init and the forward. The initialization function will initialize any layers, learnable parameters that you may need, and the forward function defines how the input gets translated into the output. So here we're downsampling our input, performing normalization, an activation function of our choice. I believe I've chosen ReLU or some variant of it, and then our convolution, and then the same again twice. And then we add what our residual was, which is this connection from the input to the output, and return it. This is a very basic residual block, and it's kind of the foundation of a lot of, well, image classification models, and you can use it also for audio or time series classification. Then we have the attention block. Yes. And here, let me bring it up to here. So you can see here I specify this linear layer QKV, and we take as input a X and perform after normalization this linear transformation on it. What this does is takes our input and creates three linearly transformed copies of it. This is called self-attention because QKV are derived from the same signal. So they're all derived from X, our input, but they are not identical because the linear transformation performed upon them is different. Because there are different weights for each of the three Q, K, and V's. And so once done, this becomes, you just perform standard scale dot product attention. And you do this across multiple heads, meaning in our case, you're performing attention across, say, 8 different heads that you've split your input across. So you divide Q into 8 even pieces, and then same with K and V, and then perform 8 separate attentions across all of these. All right, and then, all right. You then follow this same pattern of projecting, normalizing, and then performing a feed forward. So this is the basic transformer block, is what people have kind of come to associate with the transformer, is the scale dot product attention followed by, pull it up here, followed by the feed forward. It's a basic encoder that you see in most LLMs. And so I instantiate all of these in our model, and PyTorch allows you to use nested kind of model instantiation. So if you have several modules, smaller modules, you can create a bigger module simply by instantiating them inside the large model and then calling them through your forward pass. There are a couple nuances that you have to worry about. If you create, say, if you instantiate a module inside a list, just a standard Python list, it won't be registered as a learnable parameter of this model. So you have to use something called a module list, which tells Python that, okay, this module list is an attribute of our model. We must register all the parameters inside, and this happens in a recursive way. So if you have a module list in your attention block, then when you create your model block that has an attention block in its module list, it will also register all the parameters in the module list of the attention block. And this is all done automatically. So as long as you have some basic best practices, you keep them in mind, you won't have to worry about this most of the time. Yeah, and then basically the last, so again, it's 4, I think I do 2 residual blocks without attention, and then 2 blocks with residual and attention. The idea is that you want to develop some context and expand the length of your embedding size to, say, 32 channels or something, and then perform attention. Well, the idea is that the larger the embedding, you can split it into more heads and perform multi-headed attention, where you can't do this with, say, only 2 channels. And then the output block. So if you're doing any kind of classification, you need to end up with an output of your model of the size of the number of labels you're trying to classify. So in our case, it's just REM, non-REM, and wakefulness. If you were doing in a human study, you would need REM, non-REM, REM, wakefulness, and then non-REM 1, 2, 3. So that would be what, 5, right? After this, the rest is handled by our optimizer and our criterion. So the loss function we're using for multi-class classification generally is cross and entropy loss. And the idea is the output of this model is the probability that your input corresponds to any given class. So the highest probability, obviously, is what you classify the model as, and this loss function aims to maximize the probability of the correct class. So now we're going to get into training. So we've defined this function pre-train and fine-tune. They're essentially nearly identical. They just use different data loaders and data sets. Go through quickly. We always need to instantiate the model, the optimizer, and the data loaders. And then we iterate over the number of epochs, and then inside this, iterate over the entire data set. So here's where we're going to get into the conversion process of your code to accelerate and how you can do distributed training. So this is very simple. Everything here, and I'll mark it with a little comment. Should have done this before, but that's okay. You're going here. These 4 lines are what you have to add to allow your code to do accelerated training. What this means is this is something that you only have to do if you're running in a Jupyter Notebook. It's some bug that I found. You don't have to worry about this generally. But otherwise, this project config just specifies what directory you want to save your model to, and whether you want to have automated checkpoint naming. Either a couple other parameters you can specify, but this is the important part, the accelerator. So conceptually, what the accelerator does is splits the data set into however many number of GPUs you have. So if you have 4 GPUs, you're going to be splitting your data into 4 equally sized chunks and then doing training on each of those separately. This allows you to theoretically train your model 4 times faster. Of course, it doesn't happen exactly. You don't get 4x speed boost because there is some overhead with communication between the different threads. But you should see significant improvements, and Accelerate does this automatically using this prepare function. So you pass in your data loaders, your model, and your optimizer, and it splits your data loaders across the GPUs and threads, and copies your model across all of them. So this is something known as data parallelization, and this is distinct from model parallelization. So for most cases, people who want a speed boost or want to be able to fit large data onto multiple GPUs will use this method. Model parallelization is where your model is too big to fit on a single GPU. This makes it hard, impossible to train on just one GPU. That's a more advanced technique because then you have to manually split your model across several GPUs and communicate between those GPUs within one iteration, within one forward pass and your backward pass. It's possible, and if you have specific needs for that, you can definitely contact me and I'll try and help implement that for you guys. But in the meantime, I feel like this will cover the majority of the use cases. and it's extremely easy to do. So afterwards, your code remains nearly identical, and you just change your what was loss dot backward in your original PyTorch code is now accelerator dot backwards, and you're calling it loss. What this does is synchronizes the backward pass between all the different GPUs you're using, and synchronizes this optimization step so that you can have it essentially enables you to train across multiple GPUs. So you update your model parameters in a cohesive way. You're not, working on shared memory simultaneously across multiple threads. I can get into some more details of these steps here. They're generally pretty well documented for any PyTorch tutorials you're doing. Conceptually, you're just inputting your sample, your batch into the model, getting some predictions from the model, passing it into your criterion, which we specified as cross entropy loss, and optimizing based on this backward pass through the model. So the loss, if poor, will direct your model downward in the direction of lowering this loss function. I mean, it's known as backpropagation. I don't know the experience in the room, so maybe let me think. So I can go a little more conceptual here then. So you're trying to optimize for a loss function. This loss is how well your model performs. It's a single scalar value that determines whether your model is making the correct predictions or not. It's different from accuracy, for example, because you can pass a gradient through it, meaning all the operations you did in your model and in your loss function are differentiable. This allows you to pass a gradient through the model to determine the gradients. So you establish a gradient for each parameter relative to your loss function, and this gradient tells you in which direction the parameter needs to move in order to, or change in order to improve the performance of the model or improve the loss, in this case, decrease the loss. And so this is the point of calculating the loss here and then performing a backward pass. This backward pass calculates the gradients for every parameter in your model, and then the optimizer performs a step in the correct direction of the gradient that has been calculated. Is that, yes? Yeah, so in this case, because we can store every batch, like a single batch on each GPU, all we're doing is calculating the we're doing the whole backprop process on each GPU individually and updating the parameters serially. So it I mean, you can think of it that way. You can also think of it as you perform backprop on, say you have 4 batches for each of the 4 GPUs. Think of it as one GPU calculating the first batch, then the next batch, then the next batch, then the next batch. It's just backprop. It's the same math as doing it serially, but instead you're doing all the propagation and forward pass at the same time. So it saves speed in that manner. But when you're actually changing the model parameters, obviously you're going to have to do this serially because you can't change the parameters 4 times in parallel. There's only one model to do this on. If your batch was too large to fit on a single GPU, what you could do is something called gradient accumulation, where you do the backward pass once, don't do the optimization step, wait, and then the next GPU does their backward pass, and suppose each batch for each GPU is 8, and you have a theoretical batch size of 16. Now this accumulated gradient is your total batch gradient, and you can now do the optimization step as if it were you'd done a single backward pass for the whole batch. Does that make sense? That true, but it's only useful if you have a very large batch size that can't fit on your GPUs. You see what I'm saying? And yeah, I agree that it's optimal, but it doesn't actually give you any speed up if your batch size fits within a single GPU, right? Because you're still doing everything in parallel except for the updates to the weights of the model, which is the least computationally expensive. That's why I add this line here, disable for not on the main process. So because you're spawning multiple processes to run each of these instances of training on a GPU, you need to use special print functions. So for any output, you want to use accelerator.print. For any logging, for example, using weights and biases, you're going to use accelerator.log. And this will automatically just call the log function or the print function on only the main process, only one process. So you don't have conflicting messages or, multiple prints for each one. Make sense? Yeah, but they're all 10% done because they're all synchronized. You see what I'm saying? So keeping the bar for only this one, it will still be for everything 10% done. If you have a print or a log that depends on every process or on some output from every process, you use accelerator.gather. And as long as the input is a torch tensor, then it will concatenate every instance across the multiple processes into a single tensor. And then you can perform some accumulation step on it, like a mean or a sum. All right, let's see here. So I've kind of explained conceptually what is happening here in the main training step. We calculate some metrics for accuracy by seeing how many of the classifications are correct. And we log all of these to weights and biases. So weights and biases is super useful, essentially logging service that you can use. And I can run it so you can see what it looks like. It allows you to log, say, the performance of your model over what? Sorry. This is our model training. I've created just a progress bar so you can see how fast it's running and the progress of a single epoch. And then weights and biases keeps track of whatever you want to log. So if you log the loss of your model, it will track that, your accuracy. This run just started, but for this run, which I was training earlier, it'll log whatever you'd like. I really like this and prefer it to other tools like TensorBoard just because it, I mean, you can watch it from anywhere, at home. If you start a training run from the office, you can check the performance and terminate it if you see that you're getting poor performance. And in this case, I was. But for example, on a longer run, which I'll show you, this is kind of what you should expect to see. A drop in the loss function. This is quite fast. Increase in accuracy, and then I log some other things like total accuracy across an epoch and across a loss. Oh yeah, so that's the thing. It's just a link. So you can open it on any browser. So you don't need to open it as long as you call using accelerate, you use accelerate, and let me find the code snippet here. You initialize the tracker if you're just using weights and biases and you're not using accelerate, it's as easy as weights and biases dot init and then your project name and whatever config you have, right? And then it'll work just like TensorBoard. You log whatever dictionary you want for let's say epoch loss or accuracy, and it'll show up here. So it's way easier. I would definitely use that over TensorBoard. Weights and biases, W and B. All right. So I've trained this model already, so I'm going to stop this. Now we're going to fine tune our model. And as I said, this is just training your model on new data, maybe specific to your use case. In the context of LLMs, this is training on like a huge corpus of general text data, and then like self-supervised training, and then you can fine tune on task specific, some downstream task like semantic understanding or something, or some hand labeled data that you have. In our context, it's fairly the same. The process is the same, and I have some parameters to specify if I want to train the whole model or just the last block of the model, for example. It will run identically. And if you're using Accelerator, once you've incorporated it into your code, if you're doing this in Jupyter Notebook, you use this function accelerate.notebook launcher. If you're doing it in your CLI, if you have like a Python script with all of this code in it, then you'll call accelerate launch in your CLI and the name of your file, as well as the parameters that you want to specify. And I forgot to mention that if you are to use accelerate, you first have to specify your configuration of your machine, and it's as simple as calling accelerate launch. Oh, sorry, I'm wrong. Accelerate config. This won't work. You call accelerate config and say, I want to use 4 GPUs on a single machine. It gives you the options to do that. You can also manually input a file, but this is easier. So I'll do multi-GPU training. I'll train on one node, and I don't want any of these optimizations. 4 GPUs, all of them. And then it saves the configuration for you. Okay, and then, yeah, Fine tuning is identical, so I'm not going to go into details here. I just use the Matthias's homemade data instead of the AccuSleep data, and I launch it from here. And then we can do our testing. So I have to rerun some of these. It turns out I didn't save the checkpoint. That's unfortunate. 1 second, sorry. I guess we are gonna run the fine tuning, and it'll go pretty quickly because our fine tuning data is much smaller. Accuracy is very poor, which I'm confused about because I just trained this. Unless I'm calculating it wrong. All right. I'm going to assume I calculated it wrong and stop this. So we've here. Yeah, we've loaded our model, and when we call accelerate.savestate at the end of each iteration of our epoch, we save our model into a checkpoint folder. This checkpoint folder can be used to load the entire state of the training loaders and the model if we say get preempted in our Slurm job, or the program crashes, our server crashes, and we can start from where we left off. It also saves the model so that we can load it later on for inference, and that's what we're going to do now. So we load the model, send it to one of the GPUs we've acquired, and load the state dictionary from the checkpoint we have. Then we evaluate the model by doing only the forward pass and accumulating all the predictions into a list here that we then can do a classification report on. So it looks pretty good. We're getting an accuracy of 83% with a 92% weighted based on REM and non-REM being significantly less than wakefulness, and a confusion matrix here. So these are a couple ways that you can evaluate the performance of your model against say other iterations that you may try. One is accuracy. Obviously, weighted accuracy is useful for let's say you have a data set that skews heavily towards a single label, having a weighted or balanced accuracy metric will tell you whether or not you're making too many misclassifications of your very low occurrence label. These other metrics can come in handy for binary classification generally, and is more useful using these precisions and F1 scores. And then our confusion matrix tells us how many true positives and false positives we have. And generally you want this diagonal to be significantly higher than the rest. So that kind of brings us to the end of this. And I know this was kind of rushed and a bit just walking through code, I guess, but I'm happy to entertain questions anywhere you got confused, and yeah, maybe even improvements for following tutorials, because this is my first one. So okay, so yeah, you can use it anytime. I'd say it's a good it might be good practice at this point to just incorporate it into your code from the beginning, because you can run it with a single GPU. You can even use it to run on a CPU and your code doesn't change at all. But when you want to, you may want specifically to leverage like the capability to train across multiple GPUs and multiple nodes if your data set is huge and your training time is getting prohibitively long. So if it's taking like a day to train an epic, that's probably telling you that you might want to speed things up. And if you've done everything else, then using multiple GPUs will help. It's also super useful if your batch size is too large to fit on a GPU. So a GPU has a certain amount of video memory, VRAM, on it that you can store your tensors on. And at some point, well, you have to store your model, you have to store your optimizer state, and you have to store all the entire batch that you're using onto the GPU. And if your batch is very large, or if your input data is very large, you may only be able to store 1 or 2 samples instead of an entire batch of 16 samples onto your GPU. And then it becomes useful to train, to use multiple GPUs, say each one has 2 samples on it, and then you do gradient accumulation, which I was referring to before, calculating the backward pass for each, not performing the optimizer step until you've done so for 16 total samples across, say, 8 GPUs, and then using this accumulated gradient to perform the optimization step. So this is where it's super useful, where your data is like very large in terms of like on a per sample basis, or on just a data set size, where you need to increase your or decrease your training time a lot. Does that make sense? Yeah. That's kind of, if your model now gets to a prohibitively large size, then you run into the problem of fitting your entire model on the GPU. Then you have to move to model parallelism, which I was referring to before. You have to split your model itself across multiple GPUs and perform computations like between them. So you don't get any speed boost from that, but it lets you train like an LLM, for example. Yes.
Do you recommend a resource for understanding some of these trade-offs? We were talking a lot about how these different approaches have certain strengths, or maybe more get more out of analysis given certain circumstances. Is there a place like a repo or somewhere where you feel like someone's done a good comparison of all these approaches?
Are you talking specifically like model design choices?
Yeah, model design choices. Yeah. What kind of layer do you use? I'm sure that the literature is massive. Is there a nice compendium somewhere?
Not that I've found. And in fact, I'm gonna look into that, because I feel like that would be a great resource to have. I think the problem that it is that it is very domain specific. So unless you are working in a very well-researched, well-documented domain like image classification, which of course there are pre-trained models and standards that there have been developed, you're going to have a hard time like finding a resource that tells you definitively, oh, try this technique, try this, because it may even depend on your data and how it differs from someone else's data, right? I can't say I know of anything like off the top of my head like that. But again, it is domain specific. So if you're doing computer vision, yeah, there are tons of resources like that. Tons of blog posts that do comparisons for image classification. And generally the approach I've found works best is reading the literature. As as big as it is, this domain, for example, has a couple influential papers that say that convolutional or even like residual networks perform better than standard statistical, like using logistic regression or handcrafted features. So yeah, I can't recommend like a specific one, but I will look because I think people could benefit from that a lot.
What about for learning PyTorch?
Yeah, 100%. Yeah, I would recommend. Let me think about this. I feel like the way I learned was just the PyTorch website has great tutorials for it, for just getting a handle of this structure of data loading, preprocessing, and then model instantiation. It'll get you through all the basics there. Beyond that, I don't know that there's a great tutorial site as much as just kind of finding, yeah, like whatever you're working on, if you can see someone else has worked on it before, that's like the best way, I think, of learning this kind of thing, because it is really a lot of experimentation and trying a couple different things before you get like the performance you're looking for. So in the beginning, what I did was I acquired resources using a batch script. So here I've stored my batch script in the folder I'm working in, this sleep staging folder. Here. So this specifies all the resources I want. I wanted 4 threads for each of the 4 GPUs I'm using, 20 gigabytes of memory, and then I start my Jupyter server here. And then I will call sbatch for this. And once it runs, it will output. Hopefully this works. I'm gonna at Jupyter. Sorry, yeah, right here. So all of this won't be there when you first start it. This is what will print. It'll print essentially the URL that you're going to use to connect your either your browser using Jupyter Notebook or Google Colab to it. You're going to copy this, and I've also linked the tutorial for this in the wiki, but you've set up SSH port forwarding by doing, this will take a minute, but SSH-L, and then you're going to SSH in, and you will use the port that you specified in your batch script to link your local computer to that node through the host node. which is necessary because you can't SSH directly into that node. Yeah, and this tutorial will go through everything you need. It has, yes. This sets up port forwarding and tunneling. And then once you have that, all you do is, and I don't know which you prefer, but you can just paste that link in here and it'll open up Jupyter Notebook. Or if you want to use Jupyter Google Colab, you'll paste that link in here. That's it. Yeah. And if you have any questions doing this, running this, come to me. My email is just valmiki@mit.edu, and feel free to ask me questions. Yeah, I'm here. I guess I didn't introduce myself in the beginning, but I'm here as a resource for anyone doing computation or machine learning in the department. Yeah. Thanks for coming, guys.